Hello, I'm Michelle Munk, the Entry, Descent, and Landing Systems Capability Lead. This video accompanies the Envisioned Future Priorities package for the land thrust and the outcome entitled Enable Lunar Mars Global Access and 20-ton Payloads. We begin our package with the definition of Entry, Descent, and Landing, or EDL. This is the process of delivering a vehicle from the top of an atmosphere and landing it safely on the surface. For those bodies without an atmosphere, such as our moon, we call it deorbit descent and landing, or DDL. There are typically 3 phases of flight: hypersonic, or entry, where we have most of our heating and pressure, we're dissipating a lot of our energy, and hopefully we're guiding to our target. The descent or supersonic portion is where we start employing additional methods of slowing ourselves down, like parachutes or engines. And then landing is the subsonic portion, where we start sensing the surface and exposing our landing gear and touching down safely. This is a very critical phase of any mission, and it's very difficult to test this end-to-end on the surface of the Earth. And so we usually use a variety of test methods and computational methods to qualify our vehicles. Now, since this package is focused on future Mars missions, we'll note that to date, all U.S. Mars missions have used the same entry and descent technology from the Viking era, which is a 70-degree rigid sphere cone aeroshell and supersonic parachutes. But these technologies really break down after about 2 to 3 metric tons of landed mass. Our investments in entry, descent, and landing technologies are really focused on improving the capabilities to land large payloads very precisely on the Moon and Mars in support of our Artemis missions. On the left-hand side of the chart, you see those lunar capabilities that we're investing in that feed forward to Mars. These include precision landing, where we're investing in sensors and algorithms to be able to land precisely on the surface. And those details can be found in a separate Envisioned Futures package on 50-meter landing and hazard avoidance. So we won't cover those details here. We're also investing in retropropulsion, testing, and model validation, both in the Mars atmosphere in wind tunnels and also for lunar applications as well. So as we start landing larger systems on the Moon, we'll get retropropulsion data back from those landings. We also need to understand how those engine plumes interact with the lunar and then Martian surfaces and create hazards for nearby assets or for the landers themselves. And then underlying all of these capabilities is foundational modeling, which we validate our models through testing, through instrumenting flight vehicles, and all of this is supported by high-performance computing. So we're constantly looking at opportunities to get actual flight data or perform relevant testing on the ground so that we can improve our models and certify these upcoming vehicles. On the right-hand side of this chart, you see those Mars-specific capabilities that we'll need to land large payloads. A critical item is a large structural aeroshell to slow us down in the thin Mars atmosphere. One way to do this is using a deployable or inflatable aeroshell, which is stowed inside the launch shroud and then expands to a large surface area when we get to Mars. We're investigating the Hypersonic Inflatable Aerodynamic Decelerator, or HIAD, which will be demonstrated at the 6-meter scale in November of 2022 with the Lofted mission. From there, subsequent larger Earth flight tests can be done at high altitude to match Mars conditions. We'll also be assessing alternative aeroshell concepts that may come forward from other parts of the community. Again, like at the Moon, we want to be able to aggregate assets because those payloads that support the human mission can't all be landed at one time. So we need to place them precisely and close together. Our state-of-the-art is established by all of our previous NASA Mars landing missions. Those are depicted on this chart, beginning with the Viking missions in 1976 through the most recent delivery of the Perseverance rover in February of 2021. You can see that we have delivered on the order of a few hundred kilograms up to a little bit over 1 metric ton. We've landed a little over a metric ton on the Mars surface, but supporting human missions is going to require a leap in scale and capability to deliver 20 to 30 metric tons. First of all, we'll need a large aeroshell structure that's bigger than will fit inside a launch vehicle shroud. Next, we'll need high-speed retropropulsion because parachutes are just not effective at these scales. And then third, we need an integrated, robust guidance, navigation, and control system that operates throughout EDL to land us precisely and safely. We've increased our capability on recent Mars missions and performed hypersonic guidance and even used some precision landing technologies, but these will have to be greatly enhanced for the human missions. The figure at the bottom of the page shows to scale the Mars entry capsules that have been flown to date alongside one concept, a low LOVD concept for landing the human scale payload. This chart shows our notional maturation strategy for all of the systems and components that need to come together into these large-scale Mars vehicles. So you see right away that a lot of things need to be developed in parallel. We start on the left. The pink bars denote our current technology maturation activities, including the lofted flight test at 6 meters. The gray bars are really the maturations that have to happen in parallel in the future. Those outlined in white specifically are demonstrated at the moon for feed forward to Mars capabilities. And all these are underpinned by a computational modeling capability that really enables us to certify these vehicles end-to-end in the computer, since we can't do end-to-end testing at Earth. Now, our strategy is really centered on large-scale Earth flight tests of the hypersonic and supersonic systems. The large-scale aeroshell in the middle of the page is really the nose cap of that aeroshell. It comes together with a large-scale HIAD system of 10 and then 18 meters. Those are married with the retropropulsion system that can be tested at smaller scale on sounding rockets before the full scale is demonstrated. And then these components all are integrated into this large-scale Earth flight test. We have 2 of those planned, one at about a 10-meter scale and then one at 18 meters, which would be very close to, if not full scale, for the Mars vehicle. This chart depicts some of the major investments we have currently in those areas you saw on the previous chart. So for hypersonic decelerators, we have the lofted flight test, which will demonstrate the HIAD at the 6-meter scale. We have investments in retropropulsion, both ground testing in wind tunnels and computational model development. We have a portfolio project called Entry Systems Modeling that is advancing tools for aerodynamics, aerothermodynamics, material response, and guidance, navigation, and control. This will ultimately reduce risk in our systems and enable us to do that end-to-end certification. These tools are validated by collecting actual flight data, such as we did on the Mars 2020 vehicle, where we collected both pressure, temperature, and heat flux data that is feeding into our improved models. We're also investing in precision landing, sensors, and algorithms, and those details can be found in the Envisioned Future Priorities package that deals with 50-meter precision landing. And then finally, we're investing in Plume surface interaction understanding through ground testing in vacuum chambers, computational modeling, and also instrumenting lunar vehicles to provide us that validation data for our models. On this page, those titles that are in orange are things that are demonstrated at the moon and feed forward to Mars. And we also note that many of these projects and investments are supported by partnerships with universities and with small businesses. This chart introduces the gaps that the entry, descent, and landing community has identified that are tied to this outcome of landing 20 tons on Mars. As we identified our gaps between the state of the art and our envisioned futures, about 20 of those map to this particular outcome. And they're listed here, grouped by those headings that we had on our notional development timeline in those gray bars. The areas are in aeroshell system, ground development and scale-up of inflatable decelerators, retropropulsion, validated prediction of Plume surface interaction, and then entry systems and foundational modeling and instrumentation. Now, all the precision landing gaps are again found in the Envision Future package that deals with precision landing. Doesn't make them any less important, but they are covered separately. So the rest of the package will go into a little bit more detail on our future plans for closing these gaps. This chart starts to lay out some of the steps that we plan to take in the near and midterm to close the gaps you've seen so far in the package. Again, we have grouped these according to the development strategy in those gray bars, and precision landing details are covered in a different package. For the sake of brevity, we have grouped these for this package into those larger scale hypersonic entry systems, retropropulsion, Plume surface interaction, and then foundational modeling. And you'll see a chart on each of these that depicts more about the strategy. The green text on this chart denotes that we have investments in these areas and they're fully funded. And the yellow depicts items that will need to be invested in the future. This chart depicts our HIAD scale-up and flight testing strategy. The state-of-the-art for HIADs was established earlier with sounding rocket tests at 3-meter scale from Wallops Flight Facility. We're currently undertaking the lofted 6-meter article flight test from Vandenberg with our partners United Launch Alliance. This flight will come in from low Earth orbit, and the article will experience Mars-relevant heating and pressures. Now, beyond 6 meters, we need to do some more work on the ground and scaling up the structure and the flexible thermal protection system so it can be produced at the 18-meter scale required for Mars missions. The commercial interest in HIADs is very key to the future of the technology. Frequent use by commercial vendors for returning rocket stages or other assets from low Earth orbit or beyond will really help us in several ways. First, it will establish a vendor base and scaling up production to the 12 and then 18-meter scales. It will provide repeated flights of the system that will build confidence in its performance, and it will allow us to gather even more data from repeated flights at some Mars conditions. So the partnerships going forward are really key. I also want to mention gas generator technologies, which are very important to large articles, because instead of taking tanks of gas with us, we can use small gas generators that provide the gases that are needed to inflate these large structures. And then all of these will come together into what you saw on the previous charts, which was our large-scale flight test for Mars applications with integrated guidance, navigation, and control, and the integration of a retropropulsion system. Together, these will feed forward into the certified Mars vehicle that can then be built for humans to Mars missions. This chart depicts our retropropulsion advancement approach. Here we're leveraging the commercial rocket stage return capability that was first demonstrated in the early 2010s. Before then, we really didn't know if a rocket engine would ignite in an oncoming flow. Working with those data sets allowed us to establish that feasibility, even though the geometry of a rocket stage and our Mars vehicles are quite different. We've also been doing ground wind tunnel testing with cold gas thrusters firing through representative four-body shapes. This allows us to examine the parametric space of Mach number, thrust coefficient, and configuration. The next step is really to add combustion and chemistry into those wind tunnel tests so that we can better update our aerodynamic databases for use in simulations. Following those steps, we would move to scaled testing at high altitudes at Earth to replicate Mars conditions, such as dynamic pressure and Mach number. These would allow us to examine real engines in real flight conditions behind flight representative shapes. These could be delivered from balloons or sounding rockets. And then finally, as we've said, these systems would be scaled up and integrated with the large-scale aeroshell systems for our large-scale Earth flight test demonstrations. Well, we will note here that these data sets that are generated by retropropulsion tests are very large, and timely analysis of those will be enabled by advanced computational methods and high-performance computing architectures as well. Now, when we start talking about plume surface interaction, things get quite challenging. We know that plume surface interaction can cause cratering, heating on the base or legs of a vehicle, and also send high-speed ejecta out towards nearby assets. We've observed plume surface interactions on nearly every lander mission, but we've never made a direct measurement of it for the purposes of model validation. So the computational models that we have are very qualitative, and we need to make them quantitative in order to get to the types of risk postures that we're willing to have for human scale missions and high value assets. So what are we doing to address this? We are conducting ground testing in vacuum facilities into different types of regolith. These are very small scale tests without combustion. We need to add combustion to that equation to get our chemistry right of the plume and how it interacts with the different surfaces. And we also need to scale up. Another way of getting flight validation data for these models is to actually instrument flight vehicles. And so we're doing just that. We're starting with the small scale commercial lunar payload surfaces landers, or CLPS, which are hundreds of kilograms in scale. And we hope to, in the future, instrument larger human scale vehicles to get that more relevant flight validation data back. Again, this problem is going to require very high efficiency computational tools and computing platforms to run those on. As we've noted throughout this package, entry, descent, and landing cannot be validated end-to-end on Earth. So we use a combination of ground testing in facilities such as ballistic ranges, arc jets, wind tunnels, and others, along with high-fidelity computational capability to certify our systems. Now, as we go forward into the future and human rate these systems, our reliabilities are going to have to improve, and our uncertainties are going to have to decrease. This is an especial challenge because we have aging facilities that have inadequate instrumentation in some respects, This creates gaps in our ability to certify these human-rated systems. So our advancement approach that's reflected in our gaps is to continue investments in a robust modeling effort across all parts of EDL. This really leverages our entry systems modeling project that we currently have, and that relies heavily on university partnerships and grants, including our Access Space Technology Research Institute, which recently started. We also need to improve the ability to instrument flight vehicles to get validation data. So this means some investments in advanced instrumentation that have lower size, weight, power, and cost to enable us to instrument more often and more effectively. And finally, to improve our investment strategy in ground test facilities and diagnostics to make sure that they are in place for the long term to support this type of capability advancement. In summary, the entry, descent, and landing systems required to land 20 tons on Mars will look significantly different than what we've flown to date. We've put together a comprehensive set of gaps to guide our technology maturation efforts. The human Mars architecture studies of the past several years have indicated that a system based on HIAD and retropropulsion will close our architecture under the current assumptions. However, we'll continue to assess alternatives as new technologies and concepts emerge. We'll heavily leverage the capabilities that are developed through lunar missions, such as precision landing and hazard avoidance, and the understanding of Plume surface interaction. But the Mars-unique entry and descent systems will remain untested, so we'll have significant investments in those in the future. The modeling and simulation, which is so key to EDL certification, is going to require significant modeling advances and computing efficiencies to make sure we can develop these systems in a timely manner with high reliability. And ground and flight tests will continue to be a foundation of entry, descent, and landing. Modern instrumentation is critical, as is new and upgraded facilities and a dedicated infrastructure line to support this envisioned future. The last chart of this package contains acronyms from throughout the presentation. That concludes the content. Thank you for listening.